Okay, so Module 3, Unit 2, the Slope-Deflection Method, analyzing frames without sidesway. Okay, so if you try to recall our introduction, I discussed there the topics dealing with the slope deflection. We will be tackling your continuous beams, your frames without sidesway, and the frames with sidesway. Okay, so we are done with your Unit 1 on the analysis using slope deflection method of continuous beams, and now we will proceed with your Unit 2, analysis of frames without sidesway using slope deflection method. Okay, so in this unit, this is your learning outcome. Okay, so analyze indeterminate frames without sidesway using SDM, that is your slope deflection method. And then, of course, to formulate deflection equations based on the type of supports. Okay, and we have here your to explain what is a frame without sidesway and sidesway. We will discuss that one before we will have an example. So if we say frames without sidesway, these are the frames. Okay, with joints, all the joints that do not translate under a certain type of loading. Okay, so that frame is considered without sidesway if all the joints do not translate under certain type of loading. So if you are going to apply this type of loading or this scenario of loading onto that frame structure, and you will attest that there is no translation on all of the joints. Okay, so for example here, in this example that we will be solving later, okay, if you try to apply this loading, this red color, into our structure, this is your frame structure, you will not expect that this will translate. The joints will not translate because of course that is fixed and your type of loading is just going down, so that will just be actually this will just be bending your members, but it will not actually deflect, or it will not actually translate the joints. Okay, so that is frame without sidesway if all the joints under that certain type of loading will have no translation. And the scenario of this is that if frame joints are all supported laterally. So okay, in this case, and actually the other case is that frame is symmetrical with symmetrical loading. Okay, so your frames will be without sidesway if all the joints are supported laterally. If you say supported laterally, let's say you have here, for this, let's say you are going to load that one in any direction, but this is supported also, so that that will not deflect or that will not translate to the horizontally. Okay, then it means that even if I will load this one, let's say again there is another support here for that to resist the movement or translation horizontally in the stock part of the frame, then even if you will try to load this one in any direction, that will never translate. Okay, any joints of this will never translate. It means that is supported laterally. Okay, but in this case, this is actually not supported laterally, because if I am going to load that one, let's say I will try to put a load which is lateral loading that will push our frame to the right, then this will bend. Okay, even if these supports are fixed, that will bend if there is a lateral loading, because again these joints on top are not restricted or are not supported laterally. So again, if I am going to load this frame here laterally, then there will be a deflection or translation at joints B and C. Okay, so again, for us to have a frame without sidesway, that can be frame supported laterally, all the joints are supported laterally. And the other case is that even if that is not supported laterally, if your frame is symmetrical and that is loaded with symmetrical loading also. So this is our case in our example. This is not actually braced laterally, but okay, your frame is exactly symmetrical. Okay, if I will try to consider this middle here, then compare left and right side, then that is actually symmetrical. And of course, in considering the symmetry of your frame, you need also to consider the symmetry of the reaction. So, for example, these are the dimensions, but this is fixed and that is spin. then that is actually not symmetrical, because the characteristic of support here is different from the characteristic of the support there. That is to be pinned. Okay, because if this is pinned, that will not resist the moment. Therefore, that is free to rotate. But in this part, that is restricted to rotate. Okay, so you will expect that even if this is symmetrical loading, symmetrical frame, if that support is not symmetrical with respect also to the frame, then of course that will not be considered a symmetrical loading with symmetrical frame, a symmetrical frame with symmetrical loading. So again, if these are different supports, even if the configuration is symmetrical, then you will expect that there will be a deflection or there will be translation. Okay, however, in our case, exactly symmetrical on supports and then of course the configuration, and at the same time that is loaded with symmetrical loading. If I will cut at the middle, that is the same loading on the other side. Or let's say even if there is a lateral load here, if there is another lateral load which is the same on the other side that is trying to counteract that one, then even if I will like now cut at the middle, even if there's a lateral loading, that is symmetrical, okay, at the middle of the structure. Therefore, there will be no sidesway. There will be no translation. The sidesway that we are talking about is the translation or the deflection of joints. Okay. Again, that is when we will be having frames without sidesway. This is very important for you to attest if your frame structure is without sidesway or with sidesway. Because if you will try to recall our formula on slope deflection equation, isn't it that you have there theta on the other end and theta on the other end with the delta on the equation, which the delta speaks about the relative deflection of the both ends. Okay, so if there is no, for example, if we say again relative deflection, let's say I am considering A and B. If this will bend that way, so B will be there, then there will be a deflection of point B relative to point A. So that is the deflection that we are talking about. Therefore, if this is with sidesway, then you will have that value of delta. You will be having a value of delta on our slope deflection equation. But if that is without sidesway, just like a beam, okay, so just like a beam, if that is a frame without sidesway, just like a beam, you will just be dealing with rotations. Okay, so that is again frames without sidesway. Now, let's try to have an example. So, determine the reactions of the frame shown below using your slope deflection method. Okay, so this is our frame, just almost the same as the frame that we solved before on your consistent deformation. However, the supports are a little bit different since this is fixed. Okay, I made that one fixed for that to be symmetrical. And of course, I removed there is a 10 kips here, but I removed that one. So that let's try to analyze a frame without sidesway. Okay. So again, this is your problem. That is a frame without sidesway. So we are just dealing here with theta on both ends, or rotations of joints. Okay, we will not be having in our SDE a delta. Okay, we will not be having translations. So again, just like on beams, we will first is to determine the degrees of freedom. These are your unknown rotations or deflections, but again, this is a frame without sidesway, so there is no deflection, or there is no translation, only rotations. So if I will try to actually load this one, this will be my prediction, or this could be the possible, okay? This could be the possible deflection or elastic curve of our frame. So, okay, that will sag, and this will of course bend also that way, but it will not translate since that is symmetrical loading, okay? So the effect will be counteracting each other. So there is no translation. So what we have is, we know that that is fixed. So point A and point D, if I will try to draw the tangent line there, the tangent line is exactly vertical, so there is no rotation of joint A and joint D. But if you try to look at joint B and C, okay, again, do not forget that frame, even if that will deflect or that will now be an elastic curve, the joint will still be, or the tangents of the joints will be still 90 degrees. Therefore, if the tangent is this theta b from the original configuration or position, then that should also be, this is theta b, then that should be theta b also. Since again, we consider that the frames that is still rigid, so that is still 90 degrees. There will be no adjustment or rotation. And same as theta c, so you will have here your tangents, and that should still be 90 degrees. So if that is theta c, and that will be also theta c. Okay, so these are your degrees of freedom. Therefore, our only unknown here on the displacements are rotation D and rotation C. Since we know that rotation A and rotation D are 0, and of course, this is a frame without sidesway, so there is no translation. Okay. So now, B is to calculate your fixed end moment. So if you will try to go back here, cut your members separately. So there is no loading in your AB and there is no loading in your CD. Therefore, your fixed end moment here on AB, BA, CD, and DC are all 0. Okay, there is no loading in your member. There is no member loads. But the only member that has load there is your BC. So that is your loading 2 kip per feet. Okay, these are your length for that. This is your length for that. This is 15, but again, there is no loading on your columns. So if you try to go back again on the ready formula that I gave you on your fixed end moment, this is your WL squared over 12. And again, okay, sige, let's go back there. Let's go back to that. Okay. So UDL, okay, this one. If I will make that fixed on both ends, then get the moments, then that is your fixed end moment, and this is going down, so this moment will try to resist that one, so that will try to deflect backwards. So these are your direction of moment. So this is counterclockwise. Okay, again, we will stick on our sign convention, clockwise positive. Therefore, on your left side, that is negative, in your right side, that is positive. WL squared over 12. So that is our formula for FEM of your UDL. Okay, so again, that is why we have here WL squared over 12. But again, your BC, since your BC is on the left, your point B is on the left, so that is the negative, and C is on the right, so that is positive. So positive and negative, WL squared over 12. Therefore, we will be having here, okay, our W is 2 kip per feet, and your length there is 30, isn't it? And then over 12. So your FDC on the left side, joint D, is negative 150, that is counterclockwise, and then on the right side is positive 150 kip feet. Clockwise, this is counterclockwise. Okay, so again, from your slope deflection equation, okay, so again, this is your slope deflection equation, general form. Then all you need to do is complete that one, substitute your L and then FEM if ever we have that FEM, and then of course whatever is given and unknown in our rotations. But again, we will expect that your 3 delta over L here will be 0, since there is no deflection, there is no sidesway. Okay, so MAB is 2 over 15, 2 times theta A. Okay, theta A again is 0, but theta B is unknown and delta is 0, and so on and so forth. Okay, there is no FEM for member AB, so that will just reverse, and you will have here your moment equation. Okay, and then member BC, 2 over 30, that length is 30, and then of course that joint B is your joint that we are considering, so that is 2 theta B, and that will be 2 theta C, since that is the joint we are considering in your MCB. And then of course delta are 0 also, and then of course that is your FEM. So BC is negative, and then CB is positive. And this is your resulting moment equation. And then MCD, just like MAB and BA, there is no FEM. So all we need to do is deal with the rotations, and there is no deflection. So theta C and theta C, since theta D are actually 0. Okay, we discussed that one a while ago. So these are your moment equations. Then all we need to do is formulate your equilibrium equations. This is now where we will be solving your rotations, and then, okay, put it back on your moment equations to solve for the end moments, and then of course later on we will solve for the reactions. Okay, formulate equilibrium equation, and then calculate these rotations, and then substitute it back to calculate your end moments. Okay, so just like on beams, okay, let's go back to the structure. So just like on beams, if I will summate moment at B, there is no existing moment here. Of course, that is fixed. But the moment on your member BA and BC will actually cancel out, since of course that is rigid. So there should be no excess moment at joint B, and there should be no excess moment at joint C. Okay? In your supports, we cannot summate moment there equate to 0 because there is a moment. Of course, there is the support moment. So we do not know that. That is what we do not know. That is the support. So we cannot do equilibrium at your joint A and D. So I will use B and C. And actually, that is where my degrees of freedom are found. So that is what I will use it. Okay, so at joint B, summation of moments. Therefore, what are the beams connected, or what are the end moments? So for member AB, your moment BA, and then of course your moment BC for member BC. Okay, so again, do not be confused. Do not interchange your ABBA and then BCCB. Since we are considering joint B, so all should be at joint B. So that is BA, BC. So just get your BA. So this is your BA. And then BC. That is your BC. Simplify, you will have your equation 1. And then at joint C will be your MCB and MCD. CB and CD. So CB and CD. CB and CD. Simplify, you will have your equation 2. And then of course solve simultaneously. Okay, so sorry, this should be equations. That should only be 2 equations. Sorry. I edited the beam. So okay, let's just change that one. Okay, so again, solving your equations 1 and 2 simultaneously, you will have that theta B and theta C to be. Theta B is 450 over EI, theta C is negative 450 over EI. Which actually, that is reasonable. They should be the same but opposite signs, because as we will try to attest this one, this is symmetrical, perfectly symmetrical, and the loading is perfectly symmetrical. So the joint B rotation and joint C rotation should be the same. Okay, so it means that they are only different in sign, since this is clockwise, so that is positive. From the original position to the deflected tangent is clockwise, so positive. From the original beam to the deflected tangent is counterclockwise, so negative. Since again that is our assumption. So they are the same, but only they are different signs. Now we have theta B, theta C. Go back to your MAB and so on and so forth. Solve the values of your end moments. Okay, so that's our next step. Substitute your MAB, MBA. I mean theta C, theta B. You will have here your moment equations. Okay, end moments. Okay, these are your end moments. So MAB is positive 60, so that is clockwise. MBA is positive 120, so still clockwise. And then you have your BC and CB. BC is negative 120, so counterclockwise. This should be the same but opposite sign. Why? Because they are on single joint. They are on the same joint. And only 2 member is connected at joint B, so they should actually be the same. Okay, but opposite signs. And then MCB is positive 120, and that is clockwise. And then MCD should be negative of that, which is correct. Okay, since they are connected on a single joint, which is joint C, CB and CD. And then finally, your MDC is negative 60. If you will try to look at attest your MAB and DC, okay, they should be the same rotation, or they should be the same moment, I mean, because actually symmetrical loading, symmetrical frame. So the moment here should be the same as the moment there. And then all we need to do, since that is just the end moment, all we need to do is transfer. That will be our reactions for MA and MB. So now we have these end moments. Okay, I will try to draw that one for me to know if I will later on calculate my, what we call this one, calculate my end shears, okay, since we will need the end shears for the support forces, okay, reaction forces. Okay, so again, the slide on beams from your member, transfer your moment and your shear. I mean, calculate first your shear, okay. So that is the first thing that we are going to do, compute and shear. So let's start with this. If I will submit moment at joint B, you will have here clockwise, both moment are clockwise, so 120 plus 60 is 180, and that will be counteracted by the moment of your shear at AB, okay. Again, in the first place, you do not know this VAB and VBA, but again, if you are used to this, you can actually target or the correct direction of that. But if not, then you will assume, and then later on, if that is negative, you will try to redirect. Okay, but again, since that is clockwise, so that is the only force that will counter for this to be equilibrium. So VAB will go to the right, so that will be a moment which is counterclockwise. That will be against the 120 and 60. So that is total of 180, and the only restricting there is your moment of VAB. So moment of that is 15 times VAB. So to get your VAB, 180 divided by 15 is exactly 12. Okay, VAB, we'll try to let me just check. 180 divided by 15 is yes 12. So summate horizontal, your VABA on the other side, on the top, since there are no other loading here horizontally, so that will be the same but opposite direction. Okay, now go to your member BC. Get the end moments again. I mean end shears using your end moments. I will first forget about your axial forces. Okay, later on we will solve that one from your joints. So now summate moment here. Okay, so again that is just of course equilibrium. You can check that one. So this is going up 30 and going up 30. You can check that one to be exactly the same as that total load, which is 30 times 2 is 60 divided by 2, since that is symmetrical. So actually that is 30. And then on this one, this is your end shear. So the same procedure, okay? You can actually check that one. The same procedure. So this is actually counterclockwise. So if I will take a moment here at joint C, that should be the only force that will counteract, so that is now clockwise, and again the same values, so that is 12, and the summation horizontal, that will be opposite, which is 12 also. Now how do we get again your axial forces? All you need to do is transfer your end moments and end shears on your joints. Okay, so for joint we will of course not transfer here, since later on, if we know everything on the axial and shear and the moment of this, before we will transfer to that support, so that we will get the support reactions. First is we will transfer it to your joints, connection joints. So this will go there. So VBA, we do not know this one, okay? So VBA is to the left, that will go to the right, and then moment is clockwise, that will go counter. In here, that is shear going up, it will go down, and then counterclockwise, it will go clockwise. Summate moment here, so that's why I'm saying that a while ago that the end moments of the members, if that is only 2 connected on a joint, should be the same but opposite direction, which is true. So that if I will summate moment at joint, this is joint B, okay? This is joint B, then I will summate moment at joint B, then that will cancel out, or that will be 0. There will be no excess moment, since actually there is no support here. Okay, so how about the summation horizontal and vertical? That is where I will be getting your axial forces, because actually the shear at this member BC is the axial at that member BA. Since BBC is equal to FBA, so that will counteract going up. So if I will transfer here, that is going down. So if that BBC is 30, that will be 30. So that is going down, counteract by this one, so 30. Transfer there, so FBA, FAB is 30, that will go down there, and then therefore I will counteract it by our support AB. So that is why this is 30. Okay, and then summation horizontal is your, of course, your shear here. Your shear on BA will be actually exactly the same as your axial on FBC. So if that is 12, then that will be 12. Going to the left, that will go to the right. Counteracted to the left, it will go to the right. Okay, so that will be the same here. So same thing here. Okay, so if I will transfer, since this is already complete, you have your moment, shear, and axial. That moment is clockwise, it will go counterclockwise, so your moment is clockwise, MA is clockwise. So my assumptions are correct. Again, if you do not know in the first place, if you cannot predict in the first place the correct direction, the only difference there is that you will end up with a negative, which is okay. All you need to do is redirect your direction. Okay, so my assumption here, since I already solved this one, is are all correct, so I will end up with positive answer. So again, moment is countered, that will be countered by your clockwise moment A, so that is MAB is 60, so that will be 60. VBA is to the left, since that is to the right, it will go to the left, so counteracted by a reaction up to the right. So 12, so that will be 12. So again, I already explained that. So we are good with your support reactions at A. So we will go to joint D. All we need to do is again transfer this on this one, and so with this on this one. So moment here is clockwise 120, it will go counterclockwise. Shear is going up, it will go going down. This moment here is counterclockwise, so it will go clockwise. Shear there is going to the right, so this will go to the left. Then summate the moment, so this will counteract, so that will be 0 since opposite directions, the same value. But summation horizontally, your shear on VCD will be your axial on FCB, which is actually we already solved that one here, but we can actually use that one as checking since that is 12, so that will be 12. So therefore we are correct. That's one way of checking if you are correct. All your values should coincide. And then summation horizontal, I mean vertical, the shear here, which is 30 going up, it will go down, counteracted by an axial force going up, it will be transferred as that compression. So 30, so 30, and then that will be 30, so that will be transferred below as going down, that will be counteracted by support going up, so that is going at 30, so we are correct. Now we are complete here. Your shear is to the right, to the left, counteracted by to the right reactions, 12, since that is 12. And then your moment is counterclockwise, it will go clockwise, and counteracted by a counterclockwise reaction, MD60. So again, this is a symmetrical frame, symmetrical loading, so you will expect symmetrical reactions. So 12, 12, okay, they will counteract since there is no external loading. Okay, so we are good. Summation horizontal, we are good. Summation vertical, you can check that one by, since again 2 times 30 is 60, 30 and 30, which is correct. So that will be 0. And then summation moment, the only moment that we have, let's say I will summate moment at this joint, okay, you can check that one. Summation moment at that joint, you can check that one. Okay, summation moment at this joint, any joint, summating moment, that should be the same. And actually, by merely looking at this, they are symmetrical and opposite directions. So my elastic curve is correct because this will not deflect because of the moment that will counteract. That is supposedly be bending that way, isn't it? If this is it's a pin, that will bend that way. So the bending will be from point A to point B. However, there is a moment, resisting moment at the support, so that will be the deflection here will be counteracted. So the tangent there therefore will be 0. The same thing here, since the moment here is counterclockwise, so that will try to deflect back your deflection supposedly if that is not fixed. Okay, so that is our beam here, I mean frame here. So that is your frame without Sidesway. So just like a beam, all you need to do is cut your frame into members, and then get your FEM, and then get your equation. Of course, know first your degrees of freedom, solve your end moments, end shear, and then transfer to the joint, solve for the reactions. Okay, so that is for your frames without Sidesway. So again, these are your important concepts. Analysis of frames without Sidesway is the same as analysis of continuous beams where only rotations are unknowns. Okay, so that is what I'm saying. And then of course, just like in your beams, consider a sign convention in determining FEM, which is to be followed in the results of your member and moments. So if you assume again clockwise positive, then the positive on the end moments will be clockwise. Okay, so again, stick to your sign convention. So now let's try to go in your analysis of frames with Sidesway using slope deflection. This is your unit 3. This is the last unit for your slope deflection, since I discussed before that slope deflection is only applicable on frames and beams. There is no slope deflection method on trusses because there are no moments on members of trusses. Okay, we only consider the axial forces on members of trusses. Okay, so we cannot use there your slope deflection. So again, now let's try to go with frames with Sidesway. So you will now be expecting here your delta. Okay, so these are your learning outcomes. So we will now be dealing with Sidesways, frame with Sidesway. And then of course, so first let's try to understand that it's just actually the opposite of what I explained a while ago with frames without Sidesway. So frames will undergo Sidesway if all joints are not supported laterally. Let's say again, this is our example a while ago, only that actually this is the exact example on your frames, the one that we solved in your frames on your consistent deformation. So the good thing here is that if we will solve using your slope deflection, you can compare later on. That should be the same. Okay, that should be the same. So again, there is a Sidesway here. Why? In the first place, your supports are not symmetrical, and in the first place, your forces, there is a lateral force that is not counteracted, and the most important thing there is, it's okay if this is the case, if there is a lateral support, but there is no lateral support for joint B and C. So if I will try to apply this load in your structure, then this will deflect. Your joint B and C will deflect to the right. That is expected to the right. Okay. So again, by merely looking at this, this joint B and C is not supported laterally, and there is a lateral load. So that will automatically deflect. So this is my elastic curve, and actually I made that one pin so that will be very exactly the same as your example using your consistent deformation, so that we can compare that one later on. Okay. So again, the same example. We'll be dealing with your degrees of freedom. Determine or identify your degrees of freedom. So at joint A, no translation, no rotation. So theta A there is 0. Of course, there's no translation. At joint B, okay, in the first place that will rotate. So you will have your theta B. And then at the same time, you have here, later on, I will explain that theta. At joint C, that will rotate. So you will have there your theta C. And then since that is not fixed, a while ago in our frames without Sidesway, I made that one as fixed. So there should be no theta D. But in this one, that is already pinned, so there is a theta D, or there is a rotation, okay, at joint D. So 3 rotations: theta D, theta C, theta D, theta B, theta C, theta D. And now additional there, since that there is now a Sidesway, is your delta. Okay. Why is it the same? Okay, your deflection is not actually symmetrical, but why is it the same? Because again, for frames, even if this will deflect and that will compress or elongate, these are actually minimal. Okay, this deflection here and or let's just talk about the compression or the change of length of the member. Okay, the strain on the member is actually negligible with respect to the entire length. So if that will try to bend, or this will try to bend that way, so you will have that as delta, that will be the same as your delta here. Why? Because again, the change in length of your BC to your deflected is negligible. Once again, I just exaggerated this elastic. But if you try to analyze it on the actual, that is actually negligible compared to the total length. So if that is delta, the deflection here is delta, and that will also be delta. Okay, so deflection at joint B and C is the same. But if this is, let's say, 2-story, You have here, and you have here another, which is, so therefore that, let's say that is a two-story or multi-story. And then all you need to do is the delta here is different from the delta on top, because the delta here will be added to the another delta on top. Okay, so let me just explain that one on the board, so that you, if ever you will face a multi-story, then you will not be confused. Okay, so let's say this is a frame, the same as our frame, but only that is a two-story. Okay, so actually, let's say there is a force here, okay, or there are forces, okay, then this will deflect. Let's say there is a loading here, that will also deflect. Okay, let's say this is A, B, C, D, E, F. Okay. So as you can see, there is a delta here, and there is a delta there, which is to be the same. Okay. So you can say that is delta 1. Okay, that is delta 1, and this is also delta 1. There is another delta here, but that delta is not solved, it will not be solved directly by the deflection of this frame BC and DE, because actually that is a combination. If I will try, the delta again is relative. This is relative deflection. So let's say, for example, if this is the original configuration, then that delta is, okay, let's say this is the original configuration, the delta there, if that will bend, is with respect, that delta here is with respect to the other joint. So the delta here is actually this one, with respect to the other end. So this is just delta 2. Let's say delta 2, that is delta 1, so that is delta 1. Indeed, this is delta 1. So again, the total deflection on top is a combination of the delta, or the deflection here below, together with its relative deflection on the member on top. So delta 1, delta 2. Therefore, the total deflection here, if I will summate all of that, that will be delta 1 plus delta 2, which is actually the same as this. That is delta 1 plus delta 2. Okay, so that will happen in your multi-story frames. Okay, relative deflection. So you need to be careful with your sidesways or with your deflections. Okay, so in our case, that is only one story, so that will be, of course, if that will be multi-story, higher story, then all you need to do is just summate your relative deflections. Okay, if you need the deflections, of course, on those joints. So these are our degrees of freedom. So your delta is the same. I explained that one a while ago. So that will serve as only one variable. Therefore, now we have four degrees of freedom. So we need to create 4 working equation. Okay, so that is our next target. But for us to do that, okay, we will be getting your FEM and your SDS. Okay, so your fixed end moment and your slope deflection equation, which are actually your end moments. Okay, so then in your member AB and CD, there are no member load. Okay, do not be confused with 10 kips. That is not a member load. If you see member load, that is within the length. Okay, that is exactly at the joint, so that is not a member load of DA, or that is not a member load of your BC. Okay, that is not a member load. Even if you try, okay, let's say go back to your formulas of fixed end moments. Okay, so even if you try to say, okay, this is the case, so that is exactly at the very end. So let's say that is exactly there. So your value for A is 0. So even if you have value for P and B, your values of fixed end moments, if A is 0 or B is 0, then all will be 0. So there is no fixed end moment if your force is on the support, if your load is on the support. So there is no fixed end moment. Okay, so there is no fixed end moment for our members A, B, and CD. Okay, A, B, and CD, there are no fixed end moments, so these are 0. And the same fixed end moment a while ago with your previous example, this is W L squared over 12, negative here, and then positive there. Counterclockwise, clockwise. Okay, so the same. Negative 150 and positive 150. W L squared over 12. Okay, so we have your FEM. All we need to do is, again, from your general form, substitute what we know, and then, of course, make it as a variable for those of the degrees of freedom. So I will explain this one. I explain this one. The only difference that we will be having here your delta already. Okay, we will be having your delta, and of course, isn't it a while ago that is fixed? I made it as a pin, so there's rotation at D. So that is just the slight difference in our solution a while ago. So you will have here your 3 delta over L. So all I need to do is substitute your L, which is for member AB 15, that is 15 feet. 15. And of course, 15 for CD, and 30 your BC. Okay. So again, theta A is 0. So we have only theta B and delta in this equation. Again, theta A is 0. So theta B and delta. Okay. And your BC, there is no change. That is the same as a while ago. Since actually, okay, why is it there is no delta? Okay, that is what I'm saying. Why is it there is no delta? Because actually, the location of the joint B in your deflected, in your elastic curve, is the same as your joint C. They are on the same elevation, so there is no relative deflection. Okay, so, but for example, only that in some cases, let's say your joint C will be going down. So relative to joint B, there is a deflection or a translation. So we can consider that as another delta. So if that is the case, okay guys, if that is the case again, that C goes down, then you will have here delta horizontal and delta going down, which is actually, you can call it delta 1 go horizontal and delta 2, which is the going down. But in our case, that is, there is no relative deflection of DC. Okay, so that will still be 0. This will still be 0. And the fixed moment, you have it there. So this is your moment equation. And your CD, okay, so a while ago, this theta D is 0 since that is fixed. But for this example with Sidesway, I made this one as spin, so there is now a rotation. Okay, so rotation theta D and theta D. That is the only difference in your rotation a while ago. And of course your delta. Your delta in your AB is the same as delta in your CD. So again, this delta here is for your BA, that is the relative deflection of joint B from A. And then delta here is your deflection or relative deflection of joint C from your joint B. There is none for BC. Okay. So that is the only difference. 3 over L, your length is 15. So you will have this your equation. So these are your equation. Then we will use this in to formulate your equilibrium equation to solve for those variables, the 4 variables, theta B, theta C, theta D, and delta. Where will I get that? Okay. We need to have 4 equations. So first is, we will have equation here. Summation of moment here is 0. We cannot use that since there is a moment. So summation at joint B, 0. Summation at joint C, 0. Summation at joint D, even if that is support, since that is not fixed, so summation is 0. Summation of moment is 0. Okay, so there is now a 3 available equation from this equilibrium. Joint B, joint C, joint D. So I will explain later on where we will be getting the 4th. Since again there are 4 variables, there should be 4 equations. Okay, so the summation at joint B, MBA, MBC, get your MBA, MBC. substitute, simplify, summation at joint C, CBCD, CBCD, okay, CBCD, simplify, you will have this, okay, it's up to you how you will simplify. If you want to make it decimal, as long as you will consider the almost exact values. And then summation at joint D, the only member connected to that is your DC. So that is just DC equal to 0. We will have your equation 3. Okay. Now this is a little bit different with your frame without Sidesway formulating your last equation. Okay. That is true in all examples. If you will try to see all other examples of your frames with Sidesway or try to solve, you will end up there with a missing equation, missing joint for the last equation. So we will get that one from equilibrium of the total structure. Okay. So we'll be getting a fourth equation considering it's up to you. There are some cases wherein summating moment at any joints will give you, but in our case, if I will summate at joint D and joint C, okay, what will I do? If we say whole structure, all I need to do is try to remove my supports. Okay, since actually you cannot use this total structure with support, since in the first place we do not know that one. That is what we do not know. So what we are going to do is try to cut this one just after the support. So you will try to expose your end shear and end moments. And actually end shear and end moments are what we can solve before the reaction. So cut and cut, you will expose your MAB, BAB, and of course your axial forces. But again, we cannot get your axial forces without your end shear, and we cannot get your end shear without your end moments. So we should get rid of using your axial. So if I will submit moment at joint B, I cannot do that because there will be FDC on my equation, and I do not want that one, because again I do not know where to get the value of that. Because by the way, we are trying to create equations in terms of your degrees of freedom, so that should be theta C, theta D, theta B, and delta only. So we cannot have there a lot of variables. So you cannot do it also in your joint C, since you will be exposing here your what we call this one, your axial forces. Even here you cannot do that. So if I cannot use summation of moment on the whole structure, I cannot use, of course, summation vertical, since in the first place it's hard for us to find out your FAB, since in the first place we do not know your value of VBA and BDC, and you cannot translate that one on joint, so you cannot get this one. So my only choice here is summation horizontally. Why? That is 10 kips. That is given. Okay. VAB. We do not know that one. So these are the only horizontal forces. 10 kips, VAB, BDC. So if I will summate horizontally, okay, you will have there, by the way, we do not know the direction of your end shear and end moments. So in the first place, I will assume a positive direction, since again, so that later on if you will end up negative, then all we need to do is to redirect. So I will assume that this is clockwise, and that is to the right. Okay. So, but of course, it is obvious that VAB is to the left, and VDC is to the left. So to counteract that one, but again, we are not sure of that. Okay. So we will try to assume positive, and then later on see whatever happens. Okay. So VAB, VABDC, and then 10 kips are all positive. That should be equal to 0. So summation horizontal is 0, equilibrium. And then, okay, but we cannot, of course, make use of VAB and VDC as my variable. Okay, we should put that in terms of the degrees of freedom. However, if you will try to separate your AB and CD, you will expose the partners of that. So that is VAB, that will be, there is no external load, so that will be exactly VBA. That will be your moment, okay, but actually, it's okay. It is clockwise, okay. So this is DC to the right, so DC, CD here, okay? So summate moment at joint B, you will actually cancel that one, so that we will try to bring out the value of VAB in terms of the end moments. Because your end moments, we have that here in terms of your variables. So we are good to that. Summate moment here is, okay, clockwise MAB plus clockwise MBA. Equate that one to the counterclockwise moment of VAB, which is 15 times that. So VAB is actually cross multiply 15 below MAB plus BA. Okay, so that is your VAB. So this is just algebra, guys. Okay. So summate moment at joint B, you will have there the value of VAB. Summate at joint C, you will have your VDC. So these are your values, substitute back there. So these are these. And then of course, simplify. You can simplify further to that before substituting your end moment AB, BA, CD, and DC. So all I need to do is get that one. AB, BA, CD, DC. Get that one, plug it here, and then simplify. This is just algebra. Okay, so all you need to do is combine theta B, theta C, theta D, and delta. You will have here your equation 4. Okay, equation 1, equation 3, equation 4. Then all you need to do now is solve. If you have a calculator that can solve this one, now at the same time, why not? Okay, we are not on algebra, so I will not be strict on solving this. But if you do not have calculator, then make use of your approximation. This what's that? Forgot. Okay, so now solving your 4 equations simultaneously, you will have your theta B, theta C, theta D, and delta to these values. Okay, so if you will try to check the direction, okay, theta B is clockwise, and theta D is clockwise, and then delta is positive, so that is to the right, delta deflection. Theta C is counterclockwise. Just to check, okay, if my assumption is correct. So theta B is clockwise and theta D. So from this original to the deflected is clockwise, yes, clockwise. This is clockwise. C is negative, so counterclockwise and counterclockwise. Okay, by the way, do not be confused with this. This delta, theta here is just with respect to vertical. Since that is vertical, that is the same as the vertical. So we are correct. And then the delta is going to the right, so positive. Okay. So that is our values. These are our values. All we need to do is plug these values into our end moment, since that is what we need in the first place. Okay. So plug it in. Plug it in. Then you will have your end moments. Okay. So MAB, you will have that negative, counterclockwise. MBA, positive. That should be the same as BC, but opposite side. Yes. MCD is this positive, clockwise. So CD should be the negative of that. So we're good. And then, okay, this is the another way of checking. The end moment at DC should be 0. So that if I will transfer that at the support, there should be no moment, since that is just a pin. So again, that should be 0. MDC should be 0. So MDC is 0. So we're good. Okay. So now draw that one, so that later on I will transfer here and then get your edge shears. And then just like a while ago, okay, a little bit complicated. My figures are a little bit complicated since I use the exact value, the fractional values. Okay, so all we need to do is plug in your end moment and then solve for end shear, and then using your end shear solve your supports. Okay, so the same thing as a while ago. Okay, so let's go with this. Clockwise and then counterclockwise. So summate shear here, moment here, you will have that VAB to be going to the right, which is 40/49. Summation horizontal, that will be counteracted by VBA to the left. There is no external, so that will not be affected. And then here, summate moment at that or this, you will end up with this. Okay, you will not expect that this is the same shear just like in your without sway, because your moments and moments are different. So if I will summate moment here, you will have that VBC going up to be 2115 over 79, and summate moment here that is 2625 over 79 going up. You can recheck that one by summating vertically, which is 60. If I will add this one, that is exactly 60. So we're good. And then end shear here, okay, there is no moment at your DC at 20. Okay, so summate here, you will have your shear 830 over 79. Summate moment here, you will have that, or summate horizontally, that will be going to the other side, which is 830 still. Okay, you have your end shears. Now transfer at the joint to get your action forces, since we will need that one for reactions. So this is going up, that will go down, which is your action here. Okay, and in this one, this is going up, transfer there, going down, that will be the same as your action here, which is 211. Okay, so transfer below, transfer that one below, and now you completed your end forces. Okay, you completed your end forces just after your support. So now you have your supports below, transfer that one. So we have this as counterclockwise, that will go clockwise. You have that to be going to the right, that will go to the left, going up, it will go down. So counteracted by your reactions, it will go AH. So VAB is 40 over 79. In decimal, that is 0.51. Okay. MAB is the same as MA, is equal as MA. So for 200 over 79 in decimal, 53.60. And then FAB is the same as AB, 2115 over 79 in decimal, 26.77. Okay. And in here, there is no moment again. There is no end moment. So shear is to the right, go to the left, that is DH. 830 over 79 in decimal, 10.51. And then, of course, your axial, 2625 over 79 going down, the same as DV in decimal, 33.23. So this is your, okay, so this is your values. Okay. For you to be convinced, let's try to compare that one with our result before in your consistent deformation. Okay, compare. So let me just open. Okay, let me just open my presentation for our CDM. So where is our frame? Frame. Okay. This is the result in our consistent deformation. So this is our presentation for consistent deformation. Okay. So that's it. This is MA, moment at A is 5316, 0.51, and AB is 26.77. Okay, so let's compare. So this is our result for slope deflection. Okay, so 0.51, 5316, 2677, AB is 2677. DH is 10.51, DV is 33.23. Go to our answer for now is 0.51, 10.51, 33.23. So we are the same using different methods. Okay, so that is slope deflection on frames with Sidesway. Okay, the only difference of that is we will now be having your translation. So these are your important concepts. Translation is being considered as part of displacement or as part of our degrees of freedom in the analysis of frames with Sidesway. And then, of course, the total structure should be studied if translation is possible before considering this to cut the analysis short. So what does this mean is that first try to investigate, okay, if that will have a sidesway or not, because actually you can consider it as with sidesway all of the time. But actually, if you will consider a sidesway on a frame without sidesway, you will just be having your solution longer, but you will end up later on to your delta as 0. Okay? So that you will not be wasting time and having a very, very long solution. It is always good or better for you to analyze if that is sidesway or without sidesway. So that if that is a frame without sidesway, then your solution will just be shorter. Okay? So that is analysis of frames using slope deflection method. So thank you very much. If you have a question, we will discuss that one on the next live meeting, or you can comment that below. So thank you very much for listening or watching.